Okay, great. Looks like it started recording. So welcome everybody who's joined us to another IR-SIG webinar. We're happy to have you here, especially at the end of the semester and with the JWST deadline coming up. I know it's a busy time, so it's great to see such a large turnout of people. I am going to moderate the webinar today. My name is Meredith McGregor. I am an assistant professor here at the University of Colorado Boulder and also one of the co-chairs of our IR Science Interest Group along with Mike Zemkoff at RIT. I want to start with a few instructions for the webinar. I know we're all getting really used to Zoom meetings, but it's good to go over logistics quickly so we're all on the same page. You can submit your questions during the talk by using the chat window in Zoom. If you haven't brought that up already, you can mouse to the bottom of the Zoom window and click on chat. And it'll bring up a little chat window where I'm typing instructions, but you can also use that to type questions into the speaker. At the end of the talk, we'll have a Q&A session. So either I can ask the questions to the speaker from the chat window, or if you would like to ask your question directly, you can use the raise hand feature. That's found by clicking on the participants button, and then there should be a little button that says raise hand. And then I can unmute you and allow you to ask your question directly to the speaker. So some combination thereof. You can also use the chat window to submit any feedback or comments or questions you have for our IR-SIG Leadership Council. We may have time at the end to answer a few of those. If we don't, we'll get back to you via email later. And of course, use the chat window to report any technical difficulties if something goes awry during our webinar today. The last thing to say is that this webinar is recorded, and so it will be available later on our webinar webpage. The link is in the chat window, and if you haven't checked it out recently, we have a new webpage as of about a month ago, so check out our new webpage. And with that, that's all the logistics I have to cover. So I'm very excited to introduce our speaker today, which is Tony Mroczkowski. Tony got his PhD in 2009 from Columbia University. Then he was a postdoc at the University of Pennsylvania and an Einstein Fellow at JPL and Caltech. And then he was an NRC fellow at the Naval Research Lab, and now he has been at ESO as an astronomer and submillimeter instrument scientist since early 2016, and he's done a lot of work on ALMA development. And today he's going to talk about AtLAST, the Atacama Large Aperture Submillimeter Telescope. So Tony, I'll let you take it away.
Great, thanks. Thanks for the introduction. Thanks for attending, everybody. And yeah, I'm going to talk about the AtLAST. A lot of the contributions in this have come from a lot of people, but the main sort of the core leaders of the design study that I'm going to describe here are Claudia Ciccone at Oslo, who's the head of the proposal and head of the whole design study now. Because as you know, not to give it away, but you know, we did get funded for this design study, which is really awesome. And then Pamela Clausen in Edinburgh at the Royal Observatory and UCAT-C. Okay, so outline is the motivation and the introduction to the design study, science drivers for AtLAST, galactic and extragalactic surveys. Probably all of these topics are going to be infinitely familiar to everybody on here, but I'll go over them quickly and try not to be boring to anyone. Deep extragalactic observations of the circumgalactic medium and the Sunyaev-Zeldovich effect, the design study for the telescope, and the site selection study. How I'm giving a talk right now. And the operations model and environmental sustainability study, expected outcomes of the design study, and collaboration opportunities with AtLAST. So most of you will know the science that AtLAST can do, don't worry. So astronomy at submillimeter wavelengths, this has been, Pal, stop, please. I'm trying to talk, okay? Astronomy at submillimeter wavelengths. So most of you are familiar with this. It's 7 o'clock here, by the way, for people who aren't familiar. So the kids are going crazy. It's about their bath time now. Yes, so right. You can see a picture of the galaxy here in all of the wavelengths, all of its glories. All of these are probably near and dear to the whole group here. So, I won't go into too many details, but, when you get down to the long wavelengths, you can really see the dust thermal emission and molecular content of the gas, and, learn a lot about what's going on that's, obscured in the optical. This is a typical ALMA image versus the VLT image of the same antenna galaxy, and, really bringing out what the gas is doing. And then a sort of typical comparison of what you get with a low resolution arc minute CMB survey of the South Pole Telescope. And then you follow it up with APEX, which is slightly higher resolution, but this resolves into a couple sources. And then really going with ALMA, you really resolve things into a whole cluster of sources. So that's, resolution gives you a lot, sensitivity gives you a lot, of course. So single dishes versus interferometers. A lot of people ask, we have ALMA already. Why do we need, a big single dish at the same frequencies? So interferometers are great for follow-up, but they're optimized for very narrow fields and high resolution imaging, and often narrowband spectroscopy. ALMA is only 8 gigahertz right now. And, it's basically a follow-up machine. It's a great follow-up machine. I, work for ALMA half the time. So, I'm paid to say that, but, it's true. But its mapping speed is not great. It's a very limited field of view. So if you really want to unlock new sources, you need to map larger areas, and you need a single dish for that. So the other thing about interferometers is they filter out any scales larger than what their baselines can probe. So this is another typical dish, a single dish versus interferometer, and combining the two to really bring out the full spatial dynamic range in the Orion in the Orion filament. So this took 300 pointings with ALMA, which is quite an expensive observation, involving lots of overheads. But this is something you would basically map very quickly in AtLAST. And it can also lead to underestimates of the mass of the known structures in a structure if you're filtering away all of the signal. So this is also a typical galaxy here observed by ALMA. This is the input. This is what you would see with AtLAST at 50-meter single dish. This is what the ACA would see, where you're primarily limited by the sensitivity in 10 hours. And then this is ALMA, so it's really bringing out the high resolution structure, but it's missing all of the extended scales and what's really going on. So you really need the combination of everything. And this is a large problem when you're really trying to figure out where the gas is and what phase it's in. So also there was an ESO study a few years ago, the ESO single dish working group strategy report in 2015. And a lot of this tied into, CCAT, for those of you who are involved in that. This was really, still, in the vacuum left by CCAT, we really still needed even more than ever a large single dish. So the working group report, pointed out that existing single dish facilities like APEX, like JCMT, by the late 2020s may not be so competitive anymore. And we really need reasonable upgrade paths. So, these are, the current dishes are limited by their small fields of view. Notably, the LMT is really exciting to me, but it has a 4 arc minute field of view, and that can be expanded somewhat. But, well, I don't want to give too many spoilers, but we're pushing for a much larger field of view than that with AtLAST. And the small field of view translates to a low mapping speed. So these single dishes still have faster mapping speeds than ALMA by a factor of many, often orders of magnitude. But we want really a transformative leap in the capabilities. So this is AtLAST in a nutshell. This is our basic, the basic goals and the minimum requirements for AtLAST in the design study. So these are all the frequencies covered by ALMA essentially as our goal. If we had to limit the frequencies for some reason, we would maybe cut in ALMA band 3 and higher. We want at least 40 meters, but we really want 50 meters. And this is in large part driven by the ability to actually resolve the confusion limit at 350 microns. We want a field of view of 2 degrees. We would settle for 1 degree. That's still a factor of hundreds larger than the LMT field of view, for instance. A surface accuracy of about 20 microns would enable going up to a terahertz with reasonable aperture efficiency. We'd like to enable solar observations. So ALMA has been doing a ton of solar observations that have been very interesting. But this is in a tiny field of view. This is less than an arc minute that ALMA sees in a field of view. And we could image the whole solar disk with the right instrumentation and the right surface so that you don't actually focus your sunlight and burn out your instrument, and melt everything else, like the legs of the secondary. So pointing accuracy, this, we want a very good blind pointing accuracy. We also may have additional ways of recovering better pointing when mapping fast. At least at nighttime, you might use star cameras for additional pointing accuracy. We want a fast scanning speed, at least 1 degree per second, so that we can modulate the atmospheric signal and be able to remove it. So you have to modulate your atmospheric noise faster than your astronomical signal and subtract that off. We're aiming for a site altitude of 5,100 to 5,400 meters. This is because Chilean labor law limits operations above 5,500 meters, and it would make it difficult for astronomers to get up there. We want a domeless system, if at all possible, just because it's much cheaper to build, and we think we can do it. There are a number of other domeless systems up there. And, obviously we want to be able to withstand earthquakes and snow and other events related to weather just as well, if not better, as existing facilities there. Our design study has 6 work packages. So there's a coordinator, there's a coordination committee that I'm on, but this is just because we're the ones really pushing the proposal. Not to say that there were a couple dozen people involved in contributing to the proposal, and it was truly a group effort, of course. But we have general management as work package, so WP is work package here. I lead the telescope design. It's not that I'm a specialist in designing telescopes, but we have a professional company designing the telescope, and I'm overseeing it to make sure the requirements are met. Site selection is another work package. So this will be considering logistics of building a telescope there and the weather conditions, the wind conditions, accessibility, etc. Telescope operations work package. So this is led by Avantia Hatziminaglau at ESO. Hopefully she's not on, so not hearing me butcher her name. There's a work package in environmental sustainability. So this is, we want to fully power the telescope from solar and wind and sustainable power from the start. And this is, the Atacama Desert's the most irradiance-rich place on Earth. So, solar energy is readily available there, of course. Clear skies in a high location, and it's dry. But the problem is storage, so we need to come up with a novel, perhaps battery and hydrogen gas-based storage, solution. But this is going to take some work. But fortunately, we have some engineers at Oslo. So this is led by Sabrina Satori at Oslo, and then developing the science case. So our science cases are as broad and wide as the ALMA science case Mainly, the difference is that we can do much larger surveys and we can't achieve the, micro-arc-second resolution that ALMA can, in a lot of circumstances, for sure. But even then, you might imagine a large single dish contributing a lot of collecting area to something like EHT or millimeter VLBI campaigns. So new science enabled by AtLAST. Key themes are submillimeter surveys, the most complete ever. Not to use too many pejoratives, but I think that's true. The life cycle of the local universe. So, what's happening in our galaxy, for instance. Baryon cycle in distant universe, so the same gas, but in distant galaxies, and often taking advantage of redshift for things moving into band and becoming easier in one way to observe, at least, even though they're dimmer. And then new measures of the Sunyaev-Zeldovich effect in the early universe. So this is one of our key science cases. We talked about a sort of submillimeter SDSS, but SDSS notably did not go very high in redshift. And we're talking about redshift out to formation of galaxies, of course. So for the survey science, ultra deep surveys, understanding the properties of dark matter, if you can do tomography of the universe. This is basically, many of you will be familiar with intensity mapping, which is low resolution, sort of tomography of the universe. But once you have resolution and you're individually detecting sources, you're really doing tomography of the universe, and you can really map out the distribution of stuff out to formation of large scale structure. And then, figuring out the molecular fingerprint of our galaxy, what are all the constituents, et cetera. And I should say, it's a little odd to be talking to the screen, without any feedback. So if people have questions, please feel free to interject, along the way. And let me know if I'm going too fast or too slowly or anything. So this is a comparison of AtLAST sensitivity. This was from Wayne Holland's white paper for the US Decadal Review, comparing a number of telescopes to AtLAST, and our sensitivity limit is far, far below existing capabilities, largely because of the supreme site and large field of view. So one of the really exciting things here is that we would be able to, sorry, I lost my, we would be able to detect Edgeworth Kuiper belt objects with AtLAST for the first time with this sensitivity. So that's that data point there. We would also be able to map the whole cycle of gas within galaxies. And this includes, through the Sunyaev-Zeldovich effect, mapping the hot ionized gas and in galaxies as well, because that's what the SC does. So that'll be in a couple slides. We can trace the dust composition of the universe and understand the properties of the gas, supermassive black hole feedback, so its impact on the galaxy evolution, on galaxy cluster evolution, through a number of proxies, basically measuring what the molecular output is, measuring what its impact is on the pressure profiles of these objects, et cetera. The surveying the star formation, we're beginning to get a very good understanding of the star formation history of the galaxy, but we're still limited by the small samples and low depths of the survey. So there's still a lot to unlock there, going deeper and wider in all of the surveys, of course, and mapping galaxy clusters. So for those who don't know me, I work on the Sunyaev-Zeldovich effect as my primary science. And so I like to talk about it a lot. So with coverage from 30 gigahertz to 1 terahertz, we can map out all of these different variations in the spectrum, that are due to the Sunyaev-Zel'dovich effect. So the Sunyaev-Zel'dovich effect is a scattering of the cosmic microwave background that conserves photon number and basically leads to a decrement at lower frequencies below 220 gigahertz roughly, and an increment at higher frequencies. And this is a unique signature for the thermal Sunyaev-Zel'dovich effect. The yellow is the classical, so sort of zero temperature. And this gas is, of course, 1 to 10 keV typically, but as you start to get to very hot temperatures, the spectrum changes. And, Mike Zemkov, I think, is on this talk, but he's, he could talk to you quite a lot about these nuanced effects, of course, too. But basically, for a given gas that you're looking at, the temperature shifts the spectrum quite a lot. Similarly, there's a kinetic SC effect due to motion of the gas with respect to the CMB. So here you're measuring gas motions with respect to our best reference frame in the universe. Again, not to not to overstate things, not to use grandiose terms. And then there are also these more esoteric SC effects that really haven't been constrained or measured quite yet. But as you start to get to very high electron momenta, so this is electron momentum in terms of the MEC, so relativistic momentum. And as you start to get to very relativistic momenta, you start to really shift the spectrum at high frequencies. And you can start studying exotic plasma compositions that X-ray telescopes basically can't do because they either don't have enough photons or don't get to high enough energies. So this is also really nifty stuff. This is just what a galaxy cluster looks like at multiple wavelengths. So YTSZ is the thermal Sunyaev-Zel'dovich effect. It's proportional to the integrated pressure along the line of sight. YKSZ is a proxy essentially for the motion of the gas multiplied by the momentum, by the, well, it's basically momentum of the gas. It's the motion of the gas multiplied by the opacity of the gas in electrons. But this has been a really great effect actually going down to galaxy scales as well, because often the electron opacity is a more important factor than the temperature as you get to lower temperatures, and you can start studying the gas. And we've seen that in a number of stacking experiments getting down to galaxy scales. This is the mass-weighted temperature, so that's almost what the SC probes is, mass-weighted temperature, whereas this is X-ray temperature down here. So X-ray temperature, not to go into the details too much, but it's weighted by the X-ray emission, of course, and the X-ray emission goes as density squared. So it's sort of a higher contrast temperature, but what you really want is to know what the mean temperature is of the gas, and in a mass-weighted way, and something's weighted by the number of electrons or particles that you have there, because that tracks cosmology more, and that tracks the overall distribution. Whereas here you can be affected by various cold fronts, so very cold gas and whatnot. And this is seen in the X-ray image here. This is just a bit of cold gas that's been stripped out of some halo coming by, as these things merge and form. And then this is the electron opacity, this last panel, and it's basically, if you multiply the opacity times the temperature here, you essentially get something that traces the thermal SC effect. But all of these are unique probes that are combinable and would deepen our understanding of the hot gas and galaxy clusters and groups. So yeah, also I mentioned contributions potentially of AtLAST participating in millimeter VLBI, EHT. So the sensitivity to a point source basically scales like in a baseline as the area of one telescope participating times the area of the other. Take the root of that, the frequency, the bandwidth that you have, the integration time, of course. But basically the big factor here, assuming everything else is roughly the same, for a millimeter VLBI term, is that area gets you a lot of extra sensitivity instantaneously. And you can really, instead of integrating longer, you might make more time resolved measurements of what's going on near, say, Sagittarius star, and really benefit from that large collecting area. So I would build AtLASTs everywhere in the world if I could for that kind of science case. Yeah. And so this is getting back to describing the work packages involved. So to take a step back on the AtLAST design study, we got the news on March 13th, which at least here, things were starting to lock down. It was the first day my kids were out of school and, stuck at home and all that. And we had, worked quite a lot on this proposal, as one does for large proposals, of course. And we were told incessantly by people, who deal with the grants and everything, not to expect anything, don't get your hopes up, right? And then we're on lockdown and everything's, going a little crazy with the world. And then we get the news that we were actually selected, which was surprising, as a lot of things. So anyway, we're proceeding with the design. That the design study will kick off on March 1st, 2020. We have it intentionally starting off slowly because, who knows what will happen. And a lot of this can be done remotely, including, even though it's an EU-funded design study, we welcome participation, and we have a lot of participation and supporters from across the world. So I'm leading the telescope design study, but can always use help and input on all of that. OHB is actually doing the design study. So they used to be MT Mechatronics, but now they've been taken over by this company called OHB Digital Connect. But they have years of experience with design studies and building some of our favorite telescopes now in operation. And we plan to have a design out in a couple years so we can really use this for the science forecasting in the remainder of the study and get it out as quickly as possible. I'll also note that our SPIE proceedings are on archive today if you want to take a look, but that gives you a picture of where we are at the current time. And a lot of the slides you're going to see in the next, a lot of the plots you'll see in the next slides will be from that. So these are some of the telescopes that MTM, now OHB, has designed. And you can probably look through and pick out quite a few telescopes that you recognize. So they were involved in designing some of the ALMA telescopes, for instance, and they did a design study early on for the LMT, for instance, and whatnot. This is our baseline telescope design. So it's based heavily on the LMT design. You have an enclosed backing structure to keep the temperature stable. We think we can get most of our field of view using a 12-meter secondary mirror and a 50-meter primary, obviously, because it's a 50-meter telescope. So that's mirror 1 is the 50-meter, mirror 2 is the 12-meter. Mirror 3 allows you to bring the light over here to mirror 4 and into your science instruments. We expect at least 4 Naismith mounted instruments there. So these ones don't rotate with the telescope elevation change. So M3 and M4 would co-rotate with the axis, but you could also move M3 over to this side. Hopefully you can see the pointer, and have one large field of view Cassegrain mounted telescope down here. So that would move in elevation, but that would be a sort of unblocked instrument that experiences lower loading conditions because there are fewer mirrors in the way, and would be really nifty. Just some comparisons of AtLAST. So AtLAST is the red star to other telescopes out there. So This is primary mirror diameter. There's only one other telescope in the millimeter range that's got that primary mirror diameter. The field of view, so the field of view is superseded by some of the CMB experiments and by CCAT prime and Simon's Observatory up here, which have tremendous fields of view. And this is on a log plot. So these ones down here are really tiny compared to here. And then we're a little bit, tinier than them, of course, but when you compare the product, the area times omega, so your throughput of your telescope, we could actually be competitive with CCAT prime for throughput, which would be a really transformative leap, because we would also have this resolution and really bring a lot of capabilities that are very complementary to what CCAT prime is going to be doing very soon. Our site selection activities, so this is led by Carlos de Broek at ESO, so one of my near colleagues, and we're basically looking at sites that are above 5,100 meters because we want good transmission. Transmission on the Chajnantor Plateau at 5,100 meters is already very good, even at high frequencies. This is the median transmission throughout the year. It is, of course, a little bit better at Chajnantor peak, but it's very difficult to operate at that high of an altitude. You basically wouldn't have astronomer visitors up there because you need an exception from the Chilean government to work at that high of an altitude. So that's one hindrance, and then building a 6-meter up there, CCAT prime, of course, is being built up there and they're building roads for it, but they're building it for a 6-meter, not for a 50-meter. So it's a different ballpark, sort of. And we want to use existing roads and infrastructure as much as possible, which will reduce our costs and our ecological impact when building the observatory. So we think that's the responsible thing to do for building this next generation thing. This is getting back to the design overview. So just to refresh your memory on what we're covering all those wavelengths, etc. And this is how we achieve that great field of view and reasonably high resolution. We have a vague mapping of the of how our science cases map into instruments for first light and beyond. But for the cold CGM, you can basically see almost all of these would contribute. Maybe the ultra wide field heterodyne is less direct mapping, but even then you might want a maybe 1,000 feed horn instrument that can survey spectroscopically across at least the galaxy, and also in small area surveys to go very deep and make good measurements. Multi-chroic cameras, so this is more of a CMB style camera, and I have a slide explicitly on that since I'm more from a CMB and SC background. But basically we know we can build multi-band 6-color type cameras because those are being built now or are already built, and achieve a great mapping speed with very background limited detectors. A wideband IFU, so this would be building on a lot of the direct detection spectrometer type technologies that are currently being fielded for intensity mapping experiments, balloon-borne and smaller aperture experiments. And then 1,000, oh, sorry, the ultra wideband heterodyne, I was wrong about that. That was an idea for a single pixel camera that could maybe cover all of the wideband. The 1,000 pixel heterodyne is well, I think more interesting to me actually, but this would be doing the tomography in a higher spectral resolution sense, but it's a complement in a big way to the wideband IFU. So the wideband IFU integral field unit would give you 10,000 pixels or more with a resolving power of maybe 300 or so. And I know a number of people on this talk could could tell you a lot more about wideband IFUs and direct detection spectrometers. So one question that often comes up from the detector side and the instrumentation side is, Tony, you're talking about ridiculous numbers of pixels. I mean, we are talking about, hitting megapixel regime. But if you look at the field over the last even 15 years and just make a sort of naive extrapolation, you see that you go up by a factor of 10 every 7 years in pixel counts. So we could handily hit the megapixel regime by 2030, 2032. And for a telescope that'll operate for 30 years, maybe beyond, we could really be hitting gigapixel regimes by the end of life of AtLAST. So I don't think it's so so unrealistic, actually. Maybe we won't see that in the first light, but we'll get there. Just have to keep pushing. Yeah, and actually a notable thing on this as well is we had an AtLAST meeting in January of 2018, and Jakob Bars, who played a crucial role in the design of the IRM 30 meter, stood up. He's in his 80s, and he's like, my one regret was not making the field of view larger of the IRM 30 meter. And he was crucial in designing this thing, but bolometers were single pixel in the early 90s, and they designed it with a 6 arc minute field of view, which, is visionary for that time. So maybe we're not even talking about a large enough field of view for AtLAST, but, they only recently populated the whole field with NICA 2 being built for the IRM 30 meter. So they got there, and it took time. Operations plan, we're studying this. This is Avanthia is involved in science operations for ALMA and has gained a lot of experience from there. There's also a lot of experience, good and bad, right, from any observatory, but, there's input from Apex as well. And so, hopefully we've learned what's good and what's bad and can come up with a reasonable operations model for AtLAST. And well, it's going to be a huge field of view and perform a lot of surveys. It's also, we want to make it community accessible, and we want, people to be able to propose for it as well as, perform large surveys, rather than just making a dedicated experiment type facility. The environmental sustainability studies. So we think the most responsible thing to do is to really power this sustainably from the start. And, all of the technologies moving this way, I think in 10 years, we can be confident that there will be robust field solutions, and some of them will be designed, in this as well. So we're working on our own deployable solution, but of course, taking input from all of the other developments going on. So we're not in it alone, obviously. But this could be a very exciting thing, that helps rural communities have power for the first time and do it in a way that doesn't destroy our climate and our earth. So I'm excited about that. This is an overview of how everything relates. So obviously everything's a bit interconnected, and I'm not gonna really go into the details unless there are questions about that. This is already outdated. This was last year, where we had endorsers and supporters of the decadal papers for the Astra 2020, but it's people all over the world, so various co-authors, various endorsers spread out everywhere. And, we're picking up more all the time, but please join, support us, make this thing happen, especially, since Spica got canned, since CCAT 25 meter is not happening, it's just more and more urgent that we actually build something like this and make it available to the community. And yeah, you can sign up for contributing to the work packages. Please sign up if you actually plan to contribute, but please plan to contribute. if that makes sense. And then, yeah, we're collecting the emails here. There's a Google form linked on the AtLAST site. We will have a real professional AtLAST site very soon, but it's not live yet. Right now, it's just a placeholder page on my area of my website at ESO. Right now, we're looking to hire a PhD student. So the way PhDs in Europe work is a little different than the US, where people come in with their master's and do a 3-year PhD program. But we're hiring them now, and we're also looking to hire postdocs. The ad is closed for the PhD for the extragalactic predictions, but the postdoc is open. The PhD student for environmental studies open, for environmental sustainability. The postdoc at UCAT-C will open soon. So get involved, and especially, with a telescope simulator, we want to make it realistic, have realistic atmosphere, etc. So that's a really important thing for all the forecasts. And yeah, thanks. Please ask questions.
Okay, great. Thanks, Tony, for a really great talk. Virtual round of applause. So it's time for our Q&A session for the speaker. As I said before, you can either type your question into the chat window, and then I'll read it out to Tony, and Tony can see it as well. Or if you'd like to ask your question directly of the speaker, you can use the raise hand function, which you'll find by clicking on the participants button at the bottom of the Zoom window. And I should also note, while you're thinking of your questions, that I put the link for the new SBIE proceedings paper from AtLAST into the chat window as well. So you can refer to that. Okay, so we have a hand raised. So Martin, you should be hopefully going to be on.
Hello, hi, can you hear me?
Yep, yeah, you're good.
Hi Tony, thanks for the nice presentation. Thinking about solar system science cases where we might, for example, want to detect very weak spectroscopic signatures towards very bright continuum sources. Is there anything in the specification at the moment about spectroscopic dynamic range and thoughts about, internal reflection, mitigation, standing waves, things like that, that might affect the baseline accuracy?
No. So please contribute it. I guess, Well, I mean, a lot of the optical layout will be similar to LMT. So is it a known problem with the baselines for instruments on LMT?
I'm not exactly an expert on it, but
okay.
It's just something that came up with the Venus phosphine detection, the fact that JCMT suffers from some baseline ripples. And it's pretty common in single dish telescopes when you observe a very bright continuum source that you really start to amplify those internal reflections. So it might just be something we're thinking about. As I say, I'm not really an expert.
No, it's certainly worth thinking about. I think the optics of JCMT are actually rather complicated, right? There are more than 4 mirrors in the system. Is that right?
Yeah, maybe.
Maybe. I mean, maybe. Well, hopefully we can. I mean, I'll make a note of that.
Yeah. So I just wanted to say, in general, I'm really excited about this telescope concept, and I have a few solar system ideas for comets, icy moons, things like that. So I definitely like to be involved more in that discussion.
Okay, great. Yeah, I mean, I don't know, maybe it's simplistic, but maybe something analogous to a scattering cone, would actually help with the internal reflections, because usually it's, I don't know. Well, I'd leave that to the optics experts, but we do have a number of people doing optical simulations. So I think we can get a handle on that. But it'd be great to have your contributions and input, and keep reminding us that this is an important consideration, of course.
Great, thanks.
Yeah.
Okay, additional questions for our speaker? Okay. You should be unmuted. Oh, hold on. Maybe.
JCMT has 3 mirrors.
Yeah.
Okay. Huh.
Okay.
And it still has issues with scattering and internal reflections. Okay.
Trying to unmute. For some reason, Zoom is having a fit. You should be unmuted, I think. Giovanni, if you want to go ahead.
I was wondering about, doing searches. I was wondering what your bandwidth was for doing searches of unknown redshift for high Z galaxies.
Yeah, I mean, for the direct detection spectrometers, which of course, that would just be a detection that wouldn't get you velocities or anything. But the typical direct detection spectrometer gets the better part of an octave of bandwidth for any given, central frequency, right? Okay. So, for instance, for the W-spec design, it covers 135 to 250 gigahertz all at once with a small gap around the 183 water line in the atmosphere. But yeah, I mean, that's an octave of bandwidth certainly gets you multiple unique lines at almost all of high Z. And yeah, I mean, I guess with multiple instruments, you could always go back and survey the same area to get even more detections across more bandwidth.
Great, yeah, thanks. That's important to have, yeah, great.
Yeah, I mean, it looks like ALMA will move to greatly increase its bandwidth, and that's, just in the coming years. So by 2030, I would think for the heterodyne case, you could also achieve quite a lot of bandwidth. And even in heterodyne instruments, they're getting a good fraction of an octave of bandwidth, with a single receiver as well now.
This is an important instrument on the Z machine on the LMP.
Yeah, yeah.
Okay, thanks.
Sure. Thanks.
Good luck with
Yeah, we'll need it.
Okay. Additional questions? Give people a minute. Oh, we've got 2 hands. Okay. Let's see if I can unmute. Omid, you should be unmuted.
Yes. Hi, Tony. This is Omid.
Hi.
Wonderful talk. Thanks very much. I had a question about the site altitude, the 2 options that you have on the slide. So I was thinking, what sort of considerations do you have if you end up with a site that is lower altitude in terms of the effects on the highest frequency bands, and would you still be pushing, to have say 1 terahertz band, or would the case for that be really then much more difficult to make? What is, I guess, the highest frequency? I mean, you show here 350 microns.
Yeah. Right. Well, I mean, a number of people, even on this talk, will tell you how apex often goes above a terahertz, actually, and that's at 5,100 meters. Realistically, this minimum goal for the site altitude, I don't think is, we're going to be at least at 5,100 meters unless something goes horribly wrong, right? The Atacama Astronomy Park has a lot of sites that are near roads and already 5,100 or more meters. And, I mean, if we just built it at the same site as apex or very near to apex, we'd be at that kind of altitude. The fraction of time that you actually get these high frequency observations is, you have to plan carefully for your weather. But I think that's even true, for if you're at 5,600 meters, because the weather patterns are strongly correlated.
Right.
I would, yeah, I mean, you'd probably relax the surface RMS requirement if you had to build the telescope at a slightly lower altitude. And, that would also mean that you would, target frequencies below 500 gigahertz, but there's no plan to do that. And I don't see any huge drive to do that. We want to be able to cover as much bandwidth as possible to serve as diverse a community as possible. At the same time, we don't want the niche case of, okay, we can observe at this frequency 2% of the time, so we should try to do, we should spend all of our instrumentation money on these, instruments.
Yeah, especially because high frequency instrumentation is typically much more difficult to make.
Yeah, for sure. So if you can only observe a few percent of the time, then, that's probably not going to be the driving goal. It's just sort of a value added goal, realistically speaking.
Right. Okay, thanks.
Sure. I think there's good evidence with ALMA that you can cover most of this frequency range reliably, though.
Great. Martin put a comment in the chat about the JCMT Venus observations, describing the polynomials that have to be fit and removed in order to account for the baseline.
Right. Yeah.
We have another hand raised, so go ahead.
Okay, Axel. Hi, Tony. Thanks for the nice talk. Coming again on the high redshifts measurements with multiple line detections. I mean, currently, obviously, that's all done with a chopping secondary. If you look at the 30-meter also at apex, there's simply no way doing it differently. But I assume in the telescope design with a 12-meter secondary, there won't be any chopper. So do you envision to remove in the IFU sufficiently the atmosphere, also spectrally, or what are the ideas there? Chopper wheels?
I mean, yeah, maybe we could have a chopper wheel or a nutating, quaternary or, later type mirror for there. But in large part, this drives our scanning speed. So, you even in the heterodyne instruments on ALMA, you have stability of several seconds, if not longer, in there. So if you're modulating back and forth, you have instrument stability there, and that's even more true for the direct detection instruments, bolometer based, KID based, TES squid based instruments. So we think modulating the atmospheric signal is the primary concern, and there's good evidence from the CMB type survey telescopes that if you modulate your atmosphere rapidly enough, you can remove most of the atmospheric effects. Even
but then you're talking about the IFU to detect high redshift lines, because obviously with a single pixel broadband receiver, this wouldn't work.
Yeah, right. But within an IFU, yeah, sure. Yeah. So you could still do common mode subtraction on the IFU for sure.
But I mean, to my knowledge, this hasn't been really demonstrated. So I mean,
in heterodyne.
Yeah.
Or
so certainly should require some careful investigation whether that is feasible at all.
Yeah, and I guess my experience with heterodyne is mostly limited to interferometers, where you naturally get rid of those pesky drifts and all of that. But maybe there's some trick where maybe Dickey switching or something for some of the heterodyne. Maybe there's some clever solution out there that doesn't require a 12-meter nutator, But
but I hear a little bit, I mean, is it that is decided that it will come without a chopping secondary, or is that still something you're considering?
Well, yeah, I mean, it's something we would consider if there was a realistic approach out there, but I don't know of any. If you know of a solution for that, then yes, we should consider it. But I don't see any realistic way to do it. At least naively approaching the problem.
Okay, thank you.
Yeah.
Okay. Of course, keep putting questions in the chat window or raising your hand if you have a question for our speaker. We're just about at the top of the hour. I wanted to ask a quick question, actually, Tony. Have you thought at all about like the instantaneous sort of integration time, and whether that could enable observations of, say, time variable phenomena like stellar flares and the like?
Well, the dish itself is a third the collecting area of ALMA, so it's sort of instant point source sensitivity for the same bandwidth is going to be it's going to be a third, right? So it's sort of 10 times slower instantaneously. But then if you can take advantage of bandwidth, it's easier to design a wide bandwidth instrument for a single dish than for an interferometer, just because the back end is all in one place on that instrument itself. So I would naively say yes. I guess, are you talking about blind surveys for it, or targeted observations of flaring, of stellar flares?
Let's say both. I was just
Both.
curious about the capabilities.
Sort of a like broad unbiased survey, you're naturally driven to a single dish because you can build a multi-beam instrument that has a wide field of view, right? Maybe, well, these are going to be very small objects, right? Angular size.
Yeah.
Maybe
yeah,
if you have a,
like just looking at stars, which are completely non-resolved, right? And so
right.
in some sense, you don't win with ALMA because you don't need the resolution, because you're never going to resolve the star.
Yeah, but this might be a good science case for the millimeter VLBI with ALMA and with other, millimeter VLBI elements across the Earth, right? So you take advantage, you really increase your collecting area. If you know where your object is and you just need to look at a small field of view, and then maybe you can actually get toward resolving these, I mean, that's, when you get to the sort of micro arcsecond scales. Yeah, I mean, honestly, it's not my science forte. So, I mean, I would say make the science case to make it happen, right? But yeah, I mean, I think it all comes down to collecting area. So, we would benefit a lot by combining forces with ALMA for collecting area in that kind of case.
Okay. I think we're a little over the hour, so we should probably end here. I want to thank Tony again for a really excellent talk, and also remind all of you that we have these webinars every month, roughly. So stay tuned for future IR-SIG webinars. They typically happen on Tuesdays at 1 p.m., usually the first Tuesday of every month. Please join us in the future. And if you are interested in giving a webinar, or you know someone who'd give a great webinar, please contact any of us on the IR-SIG Leadership Council with your suggestion. So let's thank Tony again, and we hope to see you at future IR-SIG events.
Yeah, thanks for participating. And thanks, everybody. Ciao.